High in the dense, layered canopy of the Southeast Asian jungle, survival depends on staying above the forest floor. This is the domain of the Chrysopelea genus. They are highly active, daytime hunters that track down small lizards and frogs along the uppermost branches. When they need to cross the canopy, they leap from branches 10 meters high, clearing horizontal distances of up to 100 meters. This deliberate, highly efficient transit method allows the snake to bypass ground-based threats entirely. To start this process, the snake slithers to the very end of a branch, dangles in a J shape, and thrusts its body into the open air. The moment it leaves the tree, it actively sucks in its abdomen and flares its ribs outward, forming a distinct C shape. This internal flexing nearly doubles the animal's width, turning a cylindrical reptile into a pseudo-concave wing. Much like the underside of a frisbee, this concave design creates a pocket that traps high-pressure air beneath it, generating continuous upward lift. But a frisbee stays level in the air for one specific reason: it spins. A flying snake does not. In fluid dynamics, dropping a long, asymmetrical, flattened ribbon through the air without any rotational spin results in a chaotic, tumbling crash. The snake has engineered its body to catch the air, yet it lacks the basic physical requirements to stay stable. To figure out how they survive the drop, researchers at Virginia Tech brought the snakes into a massive indoor arena and filmed them jumping from an 8-meter tower. They used a 23-camera motion capture system, tracking infrared markers placed precisely along the snake's spines. The data revealed a complex mid-air slithering motion that scientists now call aerial undulation. This motion consists of two parts. First, a massive lateral wave traverses all the way down the snake's body. But as we look at the data in 3D, a second motion becomes visible, a smaller up and down vertical wave occurring at the exact same time. These two waves are strictly coupled together. The vertical wave operates at exactly twice the frequency of the lateral wave. This 2-to-1 ratio ensures that the maximum out-of-plane bending happens exactly at the tightest turns of the snake's slithering shape. The snake is continuously shifting its mass to adjust to the airflow, turning its entire body into an active, morphing wing. To prove this undulation was actually keeping the animal aloft, the research team built a mathematical model of the glide. They ran a control test by simulating a drop using the snake's flattened aerodynamic C shape, but they turned the slithering motion entirely off. The moment the rigid shape catches air, a force imbalance takes over. The animal pitches forward, rolls, and fails. In the undulating model, however, the continuous three-dimensional motion constantly shifts those aerodynamic forces, keeping the snake upright and level. The concave shape is useless on its own. The mid-air slither is a life-or-death requirement to survive the fall. Undulation is a common biological tool. Snakes use it to swim through water, or like the sidewinder, to crawl across loose sand. But Chrysopelea are the only animals known to successfully undulate through the air. They took a basic crawling motion used on the forest floor and repurposed it into a three-dimensional flight control system. By mastering this synchronized movement, they evolved a behavioral wing, bypassing the need for feathers or rigid glider flaps. This physical anomaly has now captured the attention of both physicists and the United States Department of Defense. They are studying the snake's mechanics to design mechanized flying snakes, soft robots capable of aerial undulation. These robotic gliders could navigate highly cluttered, hazardous environments where traditional winged drones would get trapped. Solving the mechanics of a falling reptile provides a specific template for agile, soft-bodied drones that move through the air